Hello friends, I'm Dr. Gaurav. In this video, I will discuss about second law efficiency. Thermal efficiency and the coefficient of performance for devices are defined on the basis of first law only, and they make no reference to the best possible performance, and thus it may be misleading. The first law efficiency alone is not a realistic measure of the performance of engineering devices. To overcome this deficiency, we defined a second law efficiency as the ratio of the actual thermal efficiency to the maximum possible, that is reversible thermal efficiency under the same condition. Consider two heat engines, both having a thermal efficiency of 30% as shown in figure. You can see in the figure we are having two engines, engine A and engine B. Both are having same thermal efficiency equal to 30%, but engine A is having its source at temperature of 600 Kelvin and engine B is having its source at temperature of 1000 Kelvin. Both of these engines are having sink temperature at 300 degree Kelvin. These engines at best can perform as reversible engines, in which case their efficiency would be for reversible heat engine A. The formula of efficiency is 1 minus lower temperature divided by high temperature. So it will be 1 minus 300 divided by 600 and it will be equal to 50%. For reversible heat engine B, again the formula is 1 minus lower temperature divided by high temperature. So it will be 1 minus 300 divided by 1000 and the value of the reversible heat engine efficiency is 70%. Now, if you want to find out the second law efficiency, then the formula will be for heat engine A, it will be equal to thermal efficiency of heat engine A divided by reversible heat engine A efficiency, that is 0.3 divided by 0.5 equal to 60%. Similarly, for heat engine B, the second law efficiency will be equal to 0.3 divided by 0.7 and it comes out to be 42.86%. That is, engine A is converting 60% of the available work potential to useful work. This ratio is only 42.86% for engine B. Thus, second law efficiency is a measure of the performance of a device relative to its performance under reversible conditions. The second law efficiency can also be expressed as the ratio of useful work output and maximum possible, that is reversible work output. This is for work producing devices. This definition is more general since it can be applied to processes in turbines, piston cylinder devices, etc., as well as to cycles. Note that the second law efficiency cannot exceed 100%. We can also define a second law efficiency for work consuming non-cyclic such as compressor and cyclic such as refrigerator devices as the ratio of minimum, that is reversible work input, to the useful work input. This is valid for work consuming devices such as refrigerators and air conditioners. For cyclic devices such as refrigerators and heat pump, it can also be expressed in terms of the coefficient of performance as the ratio of the coefficient of performance divided by coefficient of performance in case of reversible. Again, because of the way we define the second law efficiency, its value cannot exceed 100%. In the above relation, the reversible work should be determined by using the same initial and final states as in case of actual process. The second law of efficiency is intended to serve as a measure of approximation to reversible operation, and thus its value should range from 0 in the worst case, that is complete destruction of exergy, to 1 in the best case, that is no destruction of exergy. With this in mind, we define the second law efficiency of a system or exergy efficiency during a process as the ratio of exergy required divided by exergy supplied, or we can say 1 minus ratio of exergy destroyed divided by exergy supplied. For a heat engine, the exergy supplied is the decrease in the exergy of the heat transferred to the engine, which is the difference between the exergy of the heat supplied and the exergy of the heat rejected. The exergy of the heat rejected at the temperature of the surroundings is 0. The net work output is the recovered exergy. For a refrigerator or heat pump, the exergy supplied is the work input, since the work supplied to a cyclic device is entirely available. The recovered exergy is the exergy of the heat transferred to the high temperature medium, which is the reversible work. For a heat pump, and the exergy of the heat transferred from the low temperature medium for a refrigerator. For a heat exchanger with two unmixed fluid streams, normally the exergy supplied is the decrease in the exergy of the high temperature fluid stream, and the exergy required is the increase in the exergy of the lower temperature fluid stream. These are the references used in the present video. Thanks. Any questions, you can write to me gaurav.catm@gmail.com.